In this slide, we'll give consistent versus inconsistent equation using A as a 2 by 2 matrix. In the first example, this is A, this is the vector x of unknown, and this is B. We have two equations. This is the first equation, and this is the second equation with the associated b's. We can therefore write the first equation as 2x plus 4y equals to 6, and the second equation as 1x plus 3y equals to 4, implying that 4y equals to 6 minus 2x, implying y equals to 6 over 4 minus x over 2. And the second equation is implying 3y is equals to 4 minus x, implying y equals to 4 over 3 minus x over 3. We can plot these two equations, and when the lines of these two equations matches, that will be the solution for the vector xy. I have plotted these two lines, red for the first equation and green for the second equation. And it shows that this equation intersect at 1, 1 coordinate. This coordinate 1, 1 is the solution of these two equations. That is, this solution satisfies both equations at the same time. And therefore we say that this system of equation is consistent. This system of equation is consistent, and not only that, it has a unique solution. That is, there is only one solution, coordinate 1, 1, that satisfies both equations. This way of solving or finding that the system of equation is consistent and unique is troublesome and difficult. Is there a simpler way? In this lecture, we have learned that by doing this, rank of A versus the rank of the augmented matrix A and B, and we check whether they are the same rank. If the rank is equal, then what happens is that we will know that the columns of B is in the column space of A, implying that the equation is consistent. We'll have a solution. Secondly, the rank of A is equals to 2, which is equals to n, and in this case implying that we'll have a unique solution. We now explore the second example, where the system of equation is consistent but has infinite solution. Again, we'll take a brute force approach and plot the first equation as well as the second equation. Let us again use the first equation in red, implying is 2x plus 4y is equals to 6, allowing us to reduce to 4y equals to 6 minus 2x. Dividing both sides by 4, the answer is 1.5 minus half x. In the second equation, we have 1x plus 2y is equals to 3, implying 2y equals to 3 minus x, implying y is equals to 1/2 minus half x. It shows that the red equation and the green equation are the same. When we plot, we will have both red line and green line on the same line. This is what we'll see. I only plotted the red line with the red equation, which is the same as the previous red line. The green line is sitting exactly on the same place as the red line. It shows that the two equations are exactly the same. All values along this line satisfy this equation, and hence we have infinite solutions. As an example, you can substitute different values of x and y, and you would still get the correct value. Is there a simpler way to solve or to check whether the system of equation is consistent and having infinite solution? Yes, there is, and it is through this criteria. We'll check the rank of A, and in this case the rank of A is equals to 1 because A has dependent rows, and in fact you can see that it has also dependent columns, and the number of independent rows and columns is only equals to 1. The number of unknown variable n is equals to 2. First, let's check for consistency. To check whether a system of equation is consistent, all we do is to check rank of A versus the rank of A augmented by B. If the rank is the same, then the system of equation is consistent. It basically says that adding B will not change the rank. Column B is in the same column space as A. In this example, A/B rank is also equals to 1. We can see this visually. This is B. In fact, columns of B is nothing but columns 1 multiplied by 3. Now to check that it has infinite solution, it is this criteria here. Number of unknown is 2, but the rank is 1, therefore we have one free variable, and therefore we have infinite solution. In the last equation, let's check out again these two equations, writing red for the first equation. 2x plus 4y is equals to 6, implying y is again as before 1.5 minus half x. What about the second equation? In the second equation, we will write 1x plus 2y is equals to 4. When we evaluate this, we get y is equals to 2 minus half x. Now what is interesting is that both of them have the same slope. They just have different intercept. Now let's draw this graph. The red line has intercept 1.5 when x equals to 0. The green line has intercept 2 when x is equals to 0. It shows, when you study this very carefully, it shows that the red line and the green line are parallel lines. They will never meet, and hence there is no solutions. Is there an easier way to find out whether the problem is consistent, or if no solution exists? There is. Instead of plotting the two graphs and checking whether they intercept, instead we check the rank of A versus the rank of A augmented with B. If the rank of A augmented with B is greater than rank of A, then implying that column B does not live in the column space of A, and implying that we'll never get columns of A multiplied or linear combination to get B. In this case, what happened is that we call this system of equation inconsistent. What is the rank of A? Well, if you use this equation, plugging in this matrix, we get 1. And we know it is 1 because if you check the first column, the second column is nothing but a multiple of the first column. What about checking its row? Again, we see that row 1 is the multiple of row 2. What about the augmented matrix? This is A, this is B. When we check the rank is 2. The rank is 2 because actually we have 2 independent rows. Although we have 3 columns, only 2 of them are independent. First column and the third column are independent. The second column is 2 times the first column. Therefore, to repeat, to check whether the system of equation is inconsistent, all we need is to check the rank of A versus its augmented matrix AB rank. And if rank of AB is greater than A, then the system of equation is inconsistent. So this concludes our discussion for consistency in a system of equations.